Hello, my dear students, and welcome back to the second part of our first lecture dealing with semiconductor material. Again, this is a review lecture in order to fulfill all the prerequisites needed for our semiconductor devices course. Now, I will start sharing my presentation slides, and I will first start with a very brief remembering with what we already have terminated in the first part of this lecture. Okay, so I think you can now see my presentation slides. This is lecture number 1, semiconductor materials. We start with material classification. We classify material based on conductivity. We said that we have a conducting material, insulating or dielectrical material, and semiconductor material. Then we try to understand why conductors are conductors and why insulators are insulators. We first start to discuss this in an atomistic isolated level. I mean, we isolate a single atom of a material, and then we study this atom either for a conductor, an insulator, or a semiconductor, and we start to correlate between the number of valency electrons, the number of electrons in the outermost energy level, and the the conductivity capability, so that we can classify materials into either a conducting material, those materials who have electrons in their outermost energy level, and they can kick it out of the atom, so this electron become a free electron, like the case of copper, or those materials who are strongly bounded electrons, so that they will never have free electrons. This is insulators, or the in-between case, which is the semiconductor materials. Then we go to the band theory, and we transfer this from an atomistic level to a material level, where we have a set of a set of atoms, neighbors together, and then these atoms form, instead of what's called the energy level, they form what's called an energy band. And this energy band, we have two important energy bands. We have what's called the valency band, where this is a partially filled energy band, and we have a conduction band, which is a total empty energy band. And the definition of free electrons is limited to the conduction band. And also we define what's called a hole, where we said that a hole is a broken bond, and the hole can exist only on the valency band. This is briefly what we have done in the first part of this lecture. Let's now turn to the second part of the lecture. Before turning to the second part, we have just a very quick information regarding something which we already have studied in the material course, which is the effective mass. Actually, I will not go into details because we already did in 2 semesters ago when we tackled together the effect of the effective mass. However, I just need to remember you a very important point that will be reflected whenever we start studying devices, which is effective mass of electrons and effective mass of holes can be determined using what's called the EK diagram. The EK diagram is a quantum output that results with the mathematical formulation of the energy band diagram. So, for example, in this case for silicon, or generally for any material, the effective mass is the second derivative of the 1 over partial E pi partial K. So you get the second derivative, and then you make one of the second derivative, I mean the reciprocal of the second derivative. Accordingly, from this graph, you can conclude that the electron mobility, because the mobility is inversely proportional to the mass. If you remember, whenever you are fatter, your mobility is lower. This is logically. So the electron mobility in silicon, for example, is higher than the hole mobility. I'm just mentioning this important note because later on in our course, I will tell you which device is more faster, the NBM transistor or the BNB transistor. You will tell me, okay, the NPN is BGT is a transistor where electron is the majority. We have N in the emitter and N in the n in the emitter and n in the emitter side and n in the collector side. So the electrons are the dominant carrier. Then in NBN, electrons are the dominating carrier, while in BNB, the holes are the dominating carrier. Accordingly, and NBN is faster. Similarly, when we are talking about MOSFETs, the N channel is faster than the P channel. Again, this is whenever silicon is a material. Okay, so this is just a small tip to memorize. Now let's go to some important note. Okay, let me return back to this slide actually. Okay, now I told you, if you remember the story, it's like this. Generally, electrons are in the valency band. Then, due to the natural embedded internal thermal energy, this energy will be transferred to the electron. If this energy is greater than the energy gap, the electron will move from the valency band to the conduction band, and then it creates a hole. The higher the energy you have, more and more electrons will jump from the valency band to the conduction band. Makes sense? Then, if I would like to determine the number of electrons in the conduction band, which should be typically equals to the number of holes in the valency band, because simply whenever you have an electron moving from the valency band to the conduction band, then there is a gap, or it's a broken bond in the valency band. This is very simple. So the number of electrons is typically equal to the number of holes. This is very, very typical, very, very standard. Okay. Then, how we should calculate just such a number? How we should calculate the number of electrons or the number of holes? Let's try to discuss this. Okay, so I will use an example. I believe I already used it 2 semesters ago, I think. So I will just stop sharing and I will start using the. Okay, there is something wrong. No, there is no nothing. Okay, let's do it. If you remember my example. Okay, perfect. Okay, that's perfect. So it's very easy to remember or to understand that. In our university, if I told you, please, my dear students, expect how many students are now in lab 011, the circuits lab. I'm just mentioning the lab because in our department, we don't have an online, an on-campus classes, either lectures or tutorials. So the only probability to have students is in labs. That's why I'm mentioning lab. Before COVID, I made the same example, but on classroom. But unfortunately, I will not be able to do it for classrooms now. Okay, so for lab 011, today is I'm recording this lecture on Sunday. Today is Sunday. So today is Sunday, and I told you what is the probability to. Oh, sorry, not what the probability. What is the total number of students now? It's now 10 a.m. morning. Why I'm recording this lecture? Okay, so simply, in order to make this guess, you make some sort of guessing. That's all. In order to make this guess, you have to know 2 important pieces of information. The first is, what is the full capacity of this lab? I mean, how many students the maximum number of students can occupy this lab at a time? Okay, so for example, I will call this N, which is the maximum number of students that can be occupied at a time. That's perfect. But this is not only the important information, because I can told you, okay, this lab can be occupied by 20 students. Perfect. That's perfect. But if I ask you how many students are in the lab on Friday, 9 a.m. morning, you will directly told me, okay, it's 0. Why? We still have the capacity. The capacity is the same. The lab is as it is. but you multiply this capacity with the probability. You say, okay, at Friday morning, the probability to find students in the lab is 0. That's why it's 20 times 0 is equal to 0, basically. So in order to make this guess, you need two main parameters. You need the allowed spaces, the occupation. I mean, the number of spaces, the available number of spaces. And you need the probability to find students. So, for example, on Sunday morning, maybe 50% occupation due to COVID, for example. So we have 20 seats, and then these 20 seats multiplied by 0.5, then we have 10 students. When it goes to, for example, 3 p.m., okay, so the probability will be somehow less. So it becomes, for example, 25%. Then you have 20 seats again times 25%. Then you have only 5 students, and so on. After 4 p.m., of course, this probability will tend to 0. As you can see, this is very important. The number of seats are constant. The probability is a variable. The lab has 20 seats. This is a fact. But on Friday, the probability is 0. On Sunday, the probability is 50%. So basically, the probability is a variable and the number of seats is a constant. This is typically what we are going to do while we are considering the number of electrons or the number of holes. Number of electrons again defined in the conduction band, and number of holes is defined in the valency band. This is typically what we are going to do. So let's do it. Okay, I think you can now okay, you need some minutes. Okay, so yes. Okay, so I have some problem with my sharing. I have to share it again because I make a wrong share most probably. Yes, I have to share this. Again, I have a problem. Yeah, it's working now. So I have my laser pointer. I think everything is working. So we need to define two functions. One representing the available states for electrons or the available states for holes. And the other represents the probability to find an electron or the probability to find an hole. Okay, let's start with the second, which is the probability. Okay, and go to this slide. If I told you what is the probability to find an electron at 0 Kelvin, I mean, what is the probability to find an electron in the conduction band? Because again, electrons are only defined in the conduction band. So what is the probability to find an electron in the conduction band at 0 Kelvin? You should think and say, okay, electron can transfer from the valency band to the conduction band due to thermal energy, which is equals to 3 over 2 kT. So when the temperature is equals to 0 Kelvin, then you don't have internal thermal energy. And accordingly, no electron will jump from here to there. And accordingly, the probability to find an electron in the conduction band at 0 Kelvin is equals to 0. That's why we have a very important quote, says that semiconductors behaves like insulators at 0 Kelvin. Because again, insulators are defined by those materials which don't have any free electrons. So basically, when you have a 0 Kelvin, you don't have a free electron in the conduction band, and then it turns to be an insulator. So you should expect the following. Let me now return back to the slides. You should expect the following. If I make a graph, this graph, this is the probability. I will call it P for this time. And this is the energy. So you have something like this. This is the conduction band, and this is the valency band. Okay. And I told you, please, let's start to plot the probability to find electrons at 0 Kelvin. Let's try to plot this function. Okay, so what if we start to plot the probability at 0 degree Kelvin? So what is the probability to find an electron in the conduction band at 0 degree Kelvin? It's typically 0. But so as far as you don't have electrons in the conduction band, totally all electrons are in the valency band. So here the probability is 1. This is again at 0 Kelvin, no probability no electrons in the conduction band, and all electrons are in the valency band directly. So in order to make it in a form of probability density function, with that, then we have to make it a continuous function. So we will plot it like this, if you remember. And then we have this, what's called the Fermi-Dirac distribution, or the function which called the f of e. It's an f of e because, as you can see, it's a function in energy. We say that we don't have electron in the conduction band, which is energy EC to infinity. However, all electrons are in the valency band, which is EV to infinity. And if you remember this important distribution in the energy band gap, we already have discussed this in the material course, if you remember. And we said that, first of all, the first impression that, okay, to Fermi and to Dirac, you did a mistake. You did a big mistake, which is you define a probability to find an electron in the energy gap. I mean, typically this region, this is an energy gap, if you remember. And you define that there is electrons, some electrons in the energy gap. Then this is wrong, because based on our knowledge, no electrons can occupy this forbidden gap or energy gap. However, based on the probability density function you defined, I mean Fermi and Dirac, you define some electrons here. Or I mean, you define that there is a probability to find an electron here. Typically, it's 100%. So, did Fermi and Dirac do a mistake? The answer simply is no. Why? Let's return back to the example of N and P, where N is the number of students and P is the probability. The example for the lab, if you remember. We say that the occupation of the lab, for example, is 20 students, and the probability is 50%, then 50% or 0.5 times 20 is equals to 10. If the probability is 100%, like this case, then it's 20 times 100 or times 1 equals to 20. Perfect. Okay, what if I told you that there is a probability to find students equals to 100%, which is typically here, 1. However, N is equal to 0. There is no places. Then, again, the output, which is the number of students, will still be equals to 0. You have a probability. That's true. Here you have a probability. But the available places is equal to 0. You don't have places for the electrons to occupy the forbidden gap. So this is a mathematical representation that did not affect the physical meaning. Due to the symmetry of the probability density function, Fermi and Dirac introduce or define that there is a 100% probability to find an electron here from what's called EF, if you remember, the Fermi level to the valency band. However, practically speaking, this 100% will be multiplied by 0. So the output will be 0, and physically nothing has been happened, which is the case. So this is just a mathematical definition. Okay. Now, this is the Fermi-Dirac at 0 Kelvin. What if, I'm here plotting the probability for electron. Don't remember, don't forget. What if we increase the temperature a bit? Then, once the temperature increases, some electrons will move from the valency band to the conduction band. So the probability to find electron will increase a bit. And accordingly, the probability to find electron in the valency band will decrease a bit. So you will have something like that. Here you have some probability to find an electron, and here it becomes less than 100%, as some electrons leave the valency band and goes to the conduction band. So let's return back to the presentation, because it will be better plotted in the presentation. Okay, so again, let's do the laser pointer. Okay, perfect. So yeah, as you can see here, this blue line represents the 0 Kelvin case, and then the green one with a little bit higher temperature. So you still have some probability here and some probability left there. Whenever you increase the temperature, which is the red one, the probability to find an electrons in the conduction band starts to increase, and the probability to find not to find electrons in the valency band decrease. Okay, so this is a function. Of course, this is a very important function that you already, I believe you already memorized before in your exam. So this is somehow a very important function. As you can see, this is the energy. As I mentioned, the Fermi-Dirac is a function in energy, and of course, it's a function of temperature, as we mentioned, because at 0 temperature you don't have electrons in the conduction band, and then by increasing the temperature, the function changes. So that's why the energy, or the Fermi-Dirac function, is function in energy and in temperature. And also we have the introduced term which called the EF, or the Fermi-level. If you remember the Fermi-level, this is the indicator to find electrons and holes. So let me speak for a few minutes about the Fermi-level, because it's very important. It's very important to know what is the Fermi-level. Okay, my listeners. So let me start to describe briefly, or maybe just remind you about what is a Fermi-level. Perfectly. Okay. So again, my old example, which is a traditional balance. Whenever you are going to buy some vegetable or fruits or whatever it is, in a very traditional balanced way, you have to, let me use the camera. Where is the camera? Okay. So you have to, perfect. You have two sets of measurements. I need the microphone. Okay. You have two sets of measurements, and there is some vertical. I need something vertical. Okay. And there is something vertical in between these two sets. If the two sets are equal, then this will be typically vertical. When it's typically vertical, that means that the two sets on the right hand side and on the left hand side are equal. Whenever there is one set weights more than the other, then the indicator will move directly toward the higher weight. So if this one is higher, it will move like this, and vice versa. So this is typically the indicator, and this is typically for the case where we have yes, I have the indicator. Okay, this is typically the case where we have our Fermi level. So the Fermi level is just an indicator. If the number of electrons equals to the number of holes, then the Fermi level will be typically inside in the middle of the energy gap. Whenever the Fermi level, whenever the number of electrons increase or the number of holes increase, which is the doping case, which we will consider after a few minutes, then the indicator will start to move either to the electrons or to the holes based on which one is larger, electrons or holes. So let's do the next step. But before going to the doping or the Fermi level, we have to remember n. What is n? The number of students. This Fermi-Dirac function is the probability to find the students. This is the probability. But you need to multiply this probability with the number of seats, which is what we call the density of states. Again, as I mentioned in our material course, this is a quantum output, which we will not attribute in. I mean, we will make it as a fixed. This data will be given in the formula sheet. You don't need to memorize. You can just use it. Most probably you will not actually use it. You will use the final formula automatically. So this is just a given. It's output from a quantum model. So it's out of scope for this module. So this is the density of states. And finally, in order to calculate the number of electrons, which is plotted in green, what we are doing is we multiply the number of seats, this function, the number of seats, multiplied by the probability to find an electron, which is again the green function. And this multiplication will result in the number of electrons in the conduction band. And in order to calculate holes, which is very important, then you multiply the number of seats for holes. Again, this is very important, my dear student. Free electrons are only defined in the conduction band. That's why the green curve is only defined with EC tends to infinity, from EC to infinity. And holes are only defined in the valency band. That's why the red curve is defined from EV to negative infinity, because holes are only in the valency band. So again, to calculate electron, you multiply Gc of E, which is the density of the states in the conduction band. C here stands for conduction. Multiplied by this green curve, then you result this one. And in order to get the red, the number of holes, you multiply the red curve, which is JV of E, where V stands for valency. You multiply it by 1 minus F of E. Because if the probability to find electrons is F of E, then the probability to find holes is 1 minus F of E, typically. And then you have this red region, which indicates the holes. So this is typically the geometrical way to, or the graphical way to represent the number of electrons and the number of holes. And basically, as we mentioned, for each electron transferred to the conduction band, you have hole created in the valency band. So typically electrons in the conduction band equals to holes in the valency band, which is the case. So generally speaking, we call this, I mentioned this in my first part, I believe. We call this what's called the intrinsic concentration. So the intrinsic concentration is a concentration of electrons or holes due to the internal thermal energy. You didn't do any external effect on the material. You pick up a silicon at room temperature. You have 10 per 10 electrons and you have 10 per 10 holes. This is the intrinsic concentration of electrons, and this is the intrinsic concentration of holes. This is something by default. And as we mentioned, makes sense that N node, which is the number of electrons in the conduction band, is equals to or equals to P node, which is the number of holes in the valency band. And this we will call both what's called the Ni, or the intrinsic concentration. Accordingly, we can introduce a very important mass action law saying that N node times P node equals Ni squared. Because N node equals Ni and P node equals Ni. So N node times P node equals Ni squared, which is very makes sense. So this is the overall behavior of the material whenever the material is intrinsic. I mean, no external effect, and the material is under what's called a thermodynamic equilibrium. I mean, you didn't apply any external voltage to the material. That's why we use the subscript node to indicate that this is a thermodynamic equilibrium condition. We don't have any external effect. Okay, perfect. Now, this is the position of the Fermi level. I just mentioned it to you a few seconds ago, that typically as the number of electrons equals to the number of holes, we have the Fermi level directly centrally in between, in an equidistance between the conduction band and the valency band. This is basically because the number of electrons here, the number of electrons equals to the number of holes. We have already studied a mathematical formula to describe this in our previous course, if you remember, in the material course. Okay, so now we consider the case where the material is intrinsic. But what if the material is extrinsic? I mean, what if we perform some sort of doping effect? So we have typically two types of doping, what's called the N-type doping and what's called the P-type doping. And let's do it in a very quick manner because I believe you're already genius in that. Okay, so this is a silicon atom. For each silicon, or this is a set of silicon atoms, not only one. For each silicon atom, we have 4 electrons in the outermost energy level, as we know. And these 4 electrons, based on our old chemical classes, we know that silicon atom involved in what's called a covalent bond with the 4 most direct neighbors. For example, for this atom, we have 1, 2, 3, and 4. We have 4 neighbors. We have 4 direct neighbors. We call them direct neighbors. And then we have, and then we have a covalent bond. So each atom of these neighbors share 1 electron with the silicon atom. So it seems for the silicon atoms that it has 8 electrons in the outermost energy level. This is what we already have learned in our chemistry classes. Perfect. So this is for the silicon atom. And then what if using a very massive force, I kick out this silicon atom in a specific, and I replace it by another atom, but it's not silicon. We call it impurity atom. This impurity atom is a 5th group, for example, atom. What I mean a 5th group atom? That means that it has 5 electrons in the outermost energy level. So if you kick out this silicon atom and you replace it by another atom with a foreign material, I mean an impurity material, then you will have this impurity material again have 5 electrons. So 4 out of 5 will be involved in the same covalent bond because this covalent bond was established based on 4 electrons. So 4 out of 5 will be involved in a bond. And then you have additional electron which has no bond. No bond, that means no attraction force, because electrons are attracted using these bonds, either covalent or ionic or whatever. So now you have an electron, an additional electron in the system that can freely move from the valency band to the conduction band. But what is very important, my dear student, is this electron will move from the valency band to the conduction band, and it will not leave a hole in a stud because there is no broken bond. Your bond is still exists. You have 4 electrons or 4 electrons. This is an additional electron. So when this electron, the red circle here, when this electron transferred to the conduction band, no broken bond exists. That's why no holes exist. And this will lead to a very, very important issue, that number of electrons in the conduction band will be greater than number of holes, because you add 1 more electron to the system without having holes. And in this case, if you remember, I believe you remember, my dear students, because you did it either in the material course or in the electronic course, we say that N is equals to ND, which is the number of doping or the number of donor atoms, and the P, which is holes, applying the mass action law, equals Ni squared over N. So, for example, if you have ND equals to 10 power 15, for example, then you have 10 power 15 electrons. And then if you substitute here, you will have 10 power 10, which is for silicon at room temperature. You have 10 power 10 square, which is 10 power 20. 10 power 20 over 10 power 15, then you have P equals to 10 power 5. So at this case, you have 10 power 15 electron and you have 10 power 5 holes. Then the number of electrons is much greater than the number of holes. This is a very important point, my dear students. So this is the case which is an N-type. So an N-type, first you have a doping with an impurity material. This impurity material related to the 5th group, I mean, it has 5 electrons, its outermost energy level. And after replacing your silicon atom with the impurity atom, which is the 5th group atom, one additional electron appears. This electron does not involved in any bond, so it's a partially free. Accordingly, this electron will jump easily from the valency band to the conduction band, increasing the number of electrons, and then as a result, the number of electrons will be greater than the number of holes. Of course, there is here some trick. Maybe we can discuss it later on, where that it's not only to increase the number of electrons, but you also decrease the number of holes. This will be illustrated when we consider the recombination effect. Okay, perfect. This is the n-type case. Let's go to the position of the Fermi level. I believe you can already guess. As we mentioned, the Fermi level is an indicator. So whenever the energy, whenever the number of electrons increase, which is the case for an n-type material, then you should expect that the Fermi level will move to be more close to the conduction band with respect to the valence band. So no more an equidistance Fermi level. Now it starts to move toward the larger number of carrier, which is electron. By the way, we call the Fermi level at an intrinsic. In some textbooks, you will find it EFI, which is indicates the Fermi level at intrinsic, or some other textbooks say it's EI, which is the intrinsic level, is the Fermi level at intrinsic. And then we have EFN and EFP, which is EFN for the electrons and EFP for the holes. But I believe that abbreviations are easily recognized, so don't worry about it. So now, whenever you have more number of electrons, then Fermi level will move toward the conduction band. The other, again, this is the graphical solution for the number of electrons, number of holes. Now, as you can see, the states are typically the same. If you make a comparison between, if you make a comparison between this graph and this graph, you will find that typically the same. The number of states are equal. If you remember, 20 seats will be kept 20 seats. It's a fact. So number of seats are still the same. However, due to the n doping, the Fermi level is shifted upward, more closer to the conduction band. So the probability to find electrons increase, the probability to find holes, which is 1 minus f of e, decrease. That's why you result with more electron than holes. This is a graphical solution to make sure that electrons increase in the case of n-type doping. Let's do the other side, which is the p-type doping. Again, the same procedure. You will kick out the silicon atom by a massive force, what we call the ion implementation, or one of the methods that we can make doping is what's called an ion implementation. And then we replace this electron by, we replace this hole, we replace this atom by an impurity atom, a foreign atom. This atom, the new atom, the green one now, is a third group atom. I mean, it has only 3 electrons in the outermost energy level. So 3 electrons were combined with 3 neighbors, and 1 neighbor will kept alone. So we have here still 1 created broken bond. We have 1 created broken bond without having a corresponding electron in the valency band. In the conduction band. So you create 1 hole in the valency band without creating an electron in the conduction band. Accordingly, the number of holes increase. As you can see, the number of holes increase, and here is again the usual relation you are using, that P equals to NA, which is number of acceptors, and N equals to NR squared over P. Of course, I'm making this in a very quick manner because I believe you already studied at least twice before. That's why I try to speed up my delivery. So this is N, which is the number of electrons. Again, here N is low, P is high. P is the number of acceptor atoms, and the Fermi level moves downward toward the larger amount of carrier, which is the holes in this case. So, this is the graphical solution. Again, the number of seats typically is the same. Nothing has been changed. 20 seats kept the 20 seats. However, the Fermi Dirac goes downward. The probability to find holes increase. The probability to find electrons decrease. More number of holes, less number of electrons, which is a p-type material. We can generally sum up our 3 conditions in this important graph. Let's start from the extremely left graph, which is the intrinsic curve case. You know that it's intrinsic from two symptoms. First, the Fermi level, which is the green line, again EFI as I mentioned, is directly in the center. So number of electrons equals to number of holes, and we can also count that we have 4 electrons and 4 holes. Of course, this is trivial, but just to demonstrate. So we have 4 electrons, 4 holes. That's why the Fermi level is typically in the center. Whenever you make an n-type doping, electrons increase with respect to holes, and the Fermi level starts to go upward. Whenever you make a p-type doping, holes increase, and the Fermi level starts to go downward. This is typical, the 3 conditions. The first one is an intrinsic condition, where there is no external effect or doping effect. The middle one is an extrinsic n-type material, and the extreme right one is an extrinsic p-type material. This is what we should know in our second part in this introduction lecture. The third part actually will be the terminating part. We will know, or we will flash back again some important theories like the degenerate and non-degenerate semiconductor material, the recombination effect, and finally the drift diffusion model, which is very, very important for our semiconductor devices here. By the third term, we will terminate the overall revision or flashbacking lecture to this module. And after that, we will start directly in our p-n junction lecture. Thank you very much, my dear students, and wishing you all the best with studying this semiconductor module as well as other modules, and see you later on in our next part, the third part in lecture number 1.